Hi everyone and welcome to lesson 9.1, day 1. Today's lesson is going to talk about triangles on the coordinate plane. So what we first want to review what we know about triangles being classified based on their side lengths and their angle measures. So a reminder with some of these, we have for instance a scalene triangle. And what a scalene triangle is a triangle where all sides are different length. An isosceles triangle, right, is a triangle that has at least two sides that are the same length. All right, we say at least two, but usually you will see this with just two because oftentimes the better classification is when it has all three sides the same length. That's when we call that an equilateral triangle. Okay. Now, angle measure then. We are classifying a triangle based on its angle measure. An acute triangle is a triangle where all angles are less than 90 degrees. An obtuse triangle has one angle greater than 90 degrees. The other two will be acute as a result, so that it still adds up to 180 degrees. And then our right triangles are a triangle that has one angle that is exactly 90 degrees. Now our equiangular triangles are a triangle with all angles the same, and we know that this means that each one would have to be 60 degrees in order for it to add up to equal 180. They put a star next to equilateral and equiangular because they go together, right? Equilateral and equiangular go together. So if one of them is equilateral, it is going to by force make it equiangular and vice versa. We know from previous units that if this is happening, all of these angles then are going to be 60 degrees as a result. So looking at these in action, we want to classify the following based on their sides/angle measures. So if we first look at example A, number 1, notice we have two sides in this that are the same, and we also see a right angle. So those two things tell us that this is a right triangle because of that right angle. That is also isosceles because we have two sides the same, a third side that is not. Number 2, we have an angle that is larger than 90 degrees, so this is going to be obtuse, and none of the three sides are the same. So we would call this obtuse because the angle is greater than 90, and then scalene because none of those three sides are the same. Last one, on this line, we have a right angle. So again, we know it's going to be right angle-wise. All three of our sides are not the same. So again, this is a scalene triangle because none of those three are the same. Down at the bottom, our next three examples, notice we have three congruent sides, three congruent angles, all measuring 60 degrees. So we would call this equilateral and equiangular. Now you may also see that officially all three of those angles are under 90 degrees. So you might also call this acute as well as equiangular. Number 5, we are given an angle bigger than 90. So this is going to be obtuse. And then we have 2 out of 3 sides that are the same. So we would call this isosceles. Last but not least, we have 3 different size sides and 3 different size angles, but all of our angles are under 90 degrees. So this one is going to be, acute. And our sides, because all 3 are different, would force this to be scalene. All right. We have some for you to try on the back. For part A, you are classifying by the angles/sides. B, what it is based on the angles, what it is based on the sides. And part C, what it is based on the angles/sides. All right, now part B is actually a review of what we did at the end of last unit. We are testing, is the following a right triangle? So essentially we are testing out, does c squared equal a squared plus b squared? Now notice in each of these, okay, this first example, we have square root of 15, square root of 7. And if you're unsure which is the bigger out of the two, since these are exact answers, square root of 15 versus square root of 7, we see that the square root of 15 is going to be bigger than the square root of 7. So we're going to make square root of 15 our c value, and we are going to check out, does c squared equal a squared plus b squared? Well, reminder, whenever we square a square root, it's like they undo each other. So that just becomes 15, and then we have 7 plus 7, which is only 14. So since these do not equal each other, this is not going to be a right triangle. Same thing in the next one. If we're not entirely sure what 3 times the square root of 23 simplifies to be, we see it's about 14.4. So our biggest side is going to be 16. So we're going to test out, how does 16 squared compare to a squared plus b squared? Well, 16 squared is 256. And then we need to be careful because 3 times the square root of 3 is squared. Okay, you want to square root both pieces. So we want to make sure when we type this in, you use parentheses appropriately because we need to make sure that we square both the 3 and the 23. Because essentially what's happening is the 3 gets squared, it becomes 9. The square root of 23 gets squared, it becomes 23. And that is 207. And then again, that's still getting added to 49. So we're checking out 207 plus 49. Is that bigger than 256? Well, it actually ends up equaling 256 exactly. So this works out that yes, this is in fact a right triangle. Now the next part is we want to classify our sides based on a picture we see on a graph. So reminder, when we are looking for side lengths, for instance, from B to C, we can just count. Since this is vertical, B to C is just 3 units, and then A to C is also just 3 units. But to find the length from A to B, we have 2 options. We can either use Pythagorean theorem or the distance formula. So on this one, I'm going to use Pythagorean theorem. Okay, because we have these 2 vertical sides. So AB squared, right, our C squared is going to equal 3 squared plus 3 squared. So AB squared equals 9 plus 9, which is 18. So AB is the square root of 18, which is about 4.24. So I'm going to write both of those down. Square root of 18, just for the exact answer, which is about 4.24. Now we can see from this info that we have 2 sides that are same, but that third side is not. So our triangle is isosceles based on those sides. And if we test out our 3 sides, I'm going to use the square root of 18. I'm going to use the exact answer so we see this a little better. We're testing out, is this a right triangle? The answer here is going to be yes, because 18 equals 9 plus 9. This checked out. It is a right triangle. Last but not least, we want to check out the perimeter. So we're going to add up 3 plus 3, and then we're going to use that approximation, 3.24. We get a total of 10.24 as our perimeter. So I would recommend rounding for the perimeter, but not so much the exact answer there. All right, let's try another one. Okay, on this one, we only have one side that's easy to count, right? 1, 2, 3. The distance from A to C is 3. Okay, so we need to make a decision to make these. You can either use the distance formula from the last page or, again, Pythagorean theorem. So I think for B to C, I'm going to use Pythagorean theorem. So I'm going to draw in a right triangle. given this would be a side length of 1, this is a side length of 4. So from B to C, that's my hypotenuse, BC squared is going to equal 1 squared plus 4 squared. So 1 squared is 1, 4 squared is 16. So B to C squared is 17. So the square root of 17 is going to be the length of that side, aka about 4.1. Okay, so this is my side, B to C, square root of 17, or about 4.1. Now A to B, all right, I'm going to choose the distance formula just so we get some practice with that. XY, XY. So reminder with the distance formula, so this is going to be the distance from A to B. I'm going to take the square root of x minus x. So x is -2, the other x is 2 squared. And I'm going to add that to y minus y. So -2 minus 2, quantity squared. So what we're going to do is we are going to plug in our values that's underneath the square root, but we're going to ignore the square root for a second. So again, -2 minus 2 quantity squared plus another -2 minus -2 quantity squared. So we see that that ends up equaling square root of 32. And now when I square root 32, I get about 5.7. Okay, so I like doing it as 2 steps because I like knowing that exact answer and that decimal. Okay, so what we see is when we have the square root of 32 equals 5.7, all 3 of these are different sizes. So our triangle is scalene. The perimeter then, if we add these 3 numbers up, is 12.8. And last but not least, if we want to check if this is a right triangle, I'm going to take my biggest side, square root of 32, aka 5.7, and I'm going to check, does it equal my other 2 sides squared when I add it together? So square root of 32 squared is 32, and then we get 17 plus 9, which is only 26. So no, these are not equal. No, this is not a right triangle. And it doesn't even look like it would be if we ignore this fact. Ignore this fact. Okay, if we look back, there does not appear to be a right angle on that triangle. Last question is for you to try. You are finding the lengths of your 3 sides to start. Okay. And then, is it a right triangle? And what is your perimeter? Thanks everyone for watching. We'll work more with these in class.